Okay, hello everybody. My name is Dmitry. I'm the moderator for today's talk. And today, Khaled Ibrahim from Lawrence Berkeley National Laboratory is going to talk about analysis and tuning of couple clusters library based on Libtensor. So Khaled, please go ahead.
Okay. So first, can you hear me clearly?
Yes, we can hear you. Voices. Yes.
Okay. So my talk today is about the effort we did to analyze and tune the coupled cluster library that we start looking at through one of the SciDAC project. And basically, the layout of my talk, I will start with brief characterization of the Libtensor and LibCC stack, both quantitative and qualitative. Basically, I will talk about the tasking library and the tasking model that is used in this library, and also the use of BLAS or the solver routines and how efficiently they use MKL libraries and others. And also I will give some brief background about the performance issues in modern architecture and how they impact the performance of this library. I will talk about the analysis we did and the performance improvement we achieved, and also future direction about how to improve this further. So probably I don't need to introduce you to the chemistry part of this library. So basically, it is for me as a computer scientist, it's just a very powerful mathematical method for quantum chemistry. And what I care about as a computer scientist is tasking the model, the programming model that is used to improve this library or to parallelize this library. And basically, it is based on tasking model. We have a main thread that do most of the task generation, and there are many worker threads that do the execution of the main kernels. And basically, these tasks are distributed across multiple layers, and that we will discuss later on. One of the biggest challenges for this library is to handle large memory footprint, and basically, because it's basically work on a single node, so they try to exploit some physical property like symmetry to improve or to reduce the memory footprint. So so in this library, we have a stack of, actually there are multiple libraries on top of each other. Each of them is responsible of one functionality. So the coupled cluster library, which is LibCC, which sits on top, basically handle try to present all chemistry equation in an easy form, probably for a chemist. And basically, this library try to generate tasks based on these equations that can be solved by another library called Libtensor, which is built on top of multiple class libraries. One of them is MKL, which I will discuss today. There is a library that is responsible about the memory management, because typically the data set does not fit in the physical memory of the most node architecture right now. So there is a customized library for managing the memory. There is another library, it's called Libutil, which is responsible for the thread management, and there is a library for handling testing and exception. So in this talk, I will try to do some quantitative analysis to where's the time is spent in each kernel, and then we get that in details. And basically, I will also try to tell where the problems are, and basically how we were able to improve the performance of this library as it is, and how to improve it further. So before going to that, I will just give you a brief introduction to factors that influence the performance of modern architecture. And the first factor is basically the locality and management of locality. And then here I'm showing in this figure a typical multi-core architecture. In this multi-core architecture, each core has its own private L1 and L2 cache, and these units are interconnected, and they share a third level of cache. By locality, we typically mean that we need to bring the data closer to the executing core so that while doing the computation, we do not go to the memory, which is hundreds of cycles away. The L1 cache is typically in the range of few cycles. Accessing an L2 cache is typically 10 to 30 cycles. If you access third level cache, you may need tens of cycles. So basically, what we typically try to do is to bring the data as close as possible to the computing core to reduce the cost of memory access. The other objective we typically try to achieve is that we try to avoid conflicts between computing cores. So if multiple cores are using the same shared L3 cache, we try to avoid having them trashing the data set of each other. So, typically if we have a very regular application, this is an easy task to do. If it is more regular, if the application has more irregular behavior, then it becomes more challenging to achieve that. The other aspect we typically look at is the workload and data distribution. So if we have a multi-core architecture, we try to distribute the workload evenly between the cores. And in this figure, I'm showing here the Hopper node, which is one of the petaflop machines on at NURSE. And we have 24 cores here. And ideally, what we would like to do is that if we have an amount of work, we need to distribute them evenly across these cores. Not only that, but also we need to distribute the data that is available, or the data that is used by all the cores across multiple memory modules. And in this architecture, we typically have multiple cores connected to one memory module, and we call this a NUMA node. And through this distribution, we get higher bandwidth to the memory because we have multiple memory controller. Also, if we are lucky and the data is in the same NUMA node, then we have also lower latency. So if core 0 here try to access the memory, then we can have much lower latency compared with the same core accessing a memory module in another NUMA node. So we typically try to architect our application such that we have most of our access to the same node and to avoid, if possible, accessing a remote NUMA node. So, the architectures that I'm going to present data about today, both of them, they have a deep cache hierarchy, about 3 levels of cache hierarchy. And also they have multi-core. The first one is Hopper. We have 24 cores there. On Carver, we have a node with 32 cores. We have 3 levels of cache hierarchy. We have a strong NUMA property. We have 4 of them in Hopper and about 8 of them in Carver. And most of the new architectures also, they have the same properties with few exceptions. So the problems I'm going to present today is mostly I'm going to talk about. I had 4 input data set that I received, but I'm going to focus mostly on the smaller ones because they do not stress the virtual memory management part, which we didn't look at closely yet. So we will talk mostly about problem 1 and 3. So now we go to the meat of our presentation. So the first thing we did is we tried to analyze the locality of the workload in Libtensor and Libutil. And in Libtensor, we tried to measure the time that's spent in different MKL routines, the locality properties, who's the caller CPU, and also we looked at workload balance issues, frequency of call, just to tell which part is the most important part to tune. We also looked at the scheduling part, trying to see how much time is spent in the creation of threads, how much time is spent in the management of the workload, and so on. So in this slide, I'm giving you just a sample of what we were collecting. So basically, here we're looking at the profiling output of problem P1 on Hopper, and basically we distinguish the calls that goes to the same solver routine by their input arguments. So we do not say that we spend that much time on DGEM, or we look at DGEM with what input parameters. And for each of these, we give them a separate signature. And for each signature, we collect information like how many times this function with the signature is called, how much time is spent there, does the runtime respect locality or not, especially NUMA locality. And basically, for the smallest problem we found that there is more than 500 signature. So there's not a single or few routines that are heavily called. So the work is distributed across many routines. Most of them are DGEM, but DGEM is called also with many input parameters. And if we look at this table, we see that the first two signatures, which are like two uses of DGEM, they constitute about 50%. But we have many cases where we have like less than 1% of the execution time, and we have large variation of the time spent on each kernel call. Some of them need millions of cycles, some of them needs a few thousand cycles. So now we had, so this was like our first step, which is to have how Libtensor is using the solver routines. The other thing we looked at is how good is that? And to know that, we need to look at MKL or the same class routine when they work in isolation. So basically, in this figure, I'm showing the impact of two things. The first one is the impact of if the data set is in the cache or not. And basically here we are doing one of these DGEMs that is used frequently in Libtensor with these input parameters. And basically, if the data is not in the cache, which is iteration 0, we typically have 1 performance. If the data reside in the cache, we get a much better performance, which is fewer execution cycles. We can remove like 30 or 40% of the execution time if the cache is warmed or the data is available in the cache. If we have 4 threads that are executing, we see that we can have more savement, like 4x improvement, almost 4x improvement. So, so the performance depends heavily on if the data was in the cache or not. The second aspect, so we're still talking about the performance in isolation. We haven't yet contrasted the performance within Libtensor compared with the performance in isolation. So if we look at, for instance, also DGEM, here I'm looking at a small problem. We looked at if we want to compute C equal A multiplied by B, and these are all matrices, and we try to put matrix C in domain NUMA node X, and matrix B in NUMA node Y, and the matrix B in NUMA, node Z. We see that that the performance is not affected much by the NUMA node that each of these matrices reside, except for matrix P, which we have strided access. And the reason for that is we are bounded by the latency. So basically, if the data reside on the a distant NUMA node, then we got penalized more if matrix P is remote. Otherwise, we may not be impacted much because there is also some hardware mechanisms that can do prefetching for remote data, and this does not help us if we have strided access. So now we collected both images. One is the performance of MKL out as standalone thing, and the performance within Libtensor. So the next step we try to do is to contrast the performance we observe within Libtensor compared with the performance of standalone behavior. And what we're seeing here is that I'm just giving one example of one use of DGEM, but this applies also to other examples as well. We see that the performance actually tends to be very similar to the call behavior. So we are not getting the best out of MKL routines. And here I'm looking at the performance of a single thread. So I'm not even talking about the parallel version where we may have a larger difference. But typically, we also exploit parallelism in Libtensor by having more worker threads, so we should not care about this much. But what we need to care about is that a larger percentage of the performance is lost because we are not observing data locality. The other thing is that here I'm showing that I tried to split the instance we invoke DGEM into instance where we observe NUMA locality, and we get like a relatively better performance compared with the one that we do not observe NUMA locality. So this was like the first challenge we identified, that the way it is built right now does not allow to get the best out of MKL, and part of it because we cannot manage locality. We cannot tell, we cannot assign the task of doing MKL to the thread that knows that the data is available, for instance, in cache. This does not tell if it's always possible to do that. It could be complicated, but in general, we cannot say I'm spending like 80% of my time in MKL or 50% of my time, so I cannot do better, because the performance, or the main message is, the performance of MKL depends heavily on the locality of the data that you are providing to the MKL library. Are you providing something that is resident in cache or not? Are you providing something that is in a nearby NUMA node or not? So all these questions affect the any plus library, including MKL. So obviously we focus on MKL because it is known for being one of the most optimized libraries. So the other thing we looked at is the performance of the tasking library, and basically the way tasking is managed in Libtensor or Libutil, which is responsible for managing tasks, is that there is a main thread that visits all the chemistry equation, create tasks, submit these tasks to a main queue, and then release interest in running, and then wait for all worker threads to do the computation. Worker threads, on the other side, they are created in the beginning, and they wait, continue spinning, waiting for something to do. Once they see that there is some work to do in the main queues, they start dequeuing that, put some task in their own local queue, and then they start dispatching these tasks to or try to execute these tasks. If all tasks are exhausted, then the worker's thread return or yield the code that they are using. So what we try to do here is to find the time that is spent on each of these tasks, both for the main thread and for the worker threads. For the main thread, we have, as we said, we have like a composition of tasks, how much it takes to do that, in queuing task, waiting for worker. We have also times for managing or moving tasks from the main queue to the local queue, sending tasks to MKL library, and time spent to perform the work, and also manage the memory. So in this figure, I'm showing the impact of workload distribution, Quanta, and basically the default setting that exists right now is the one in the middle. And here we show the time spent in the main thread, and basically it is either trying to create a task, which is the red part of it, creation of task, and there is a blue part which is waiting for all worker thread to finish their work. On the worker side, we have the time we spent in the MKL or the blast routines. We have time spent in the memory management, and there is also time spent in managing the queues. And there is another component that is dependent on the load imbalance, or like due to, because basically what I'm showing here is the average across all workers' threads. So if some of them are doing more work than others, then we see this manifest in this blue part of the bar. So so this is the decomposition of this, the execution time, and obviously the lower the execution time, the better. And here I'm showing 3 quanta for scheduling. The first one is a small quanta, so we get, so each worker get one task, try to finish executing it before trying to get another task. Here we have 4 tasks at a time, so each worker thread try to get 4 tasks at a time, and then execute them. And here we have 16 at a time. What we can observe here is that the green part, which is the time spent in the MKL, gets smaller as we get more tasks at a time. And the reason for that is we get more related tasks, so we have a better exploitation of locality. But on the other hand, we have a higher load imbalance, so the total execution time here increases instead of improving the performance. So starting from the this, which is the default value in the current implementation, we found that it is better to have a smaller scheduling quanta, so that we have a lower overhead for scheduling for executing tasks, and having a smaller load imbalance. The other thing we looked at is what if we try to improve performance by distributing the data on different NUMA domain, and we try to do this evenly, such that we can have improved performance by having more bandwidth to the memory. We didn't try to manage the locality explicitly because we didn't have enough information about the location of the data that is accessed on each task. So here, what we, in addition to having like smaller granularity for or smaller quanta for scheduling, we added the distribution of the data across different NUMA domain, and actually we were able to improve the performance further by 15%. The first optimization probably had like 30% performance improvement. Overall, we were able, by doing these two simple techniques to have a performance improvement of on Hopper by 54 to 61%. So one thing that also comes from the tasking model that is used by Libutil is that Libutil use 1 plus n tasking model, which means that you have one main thread and n worker threads. So if you have 24 cores, you have one main thread plus 24 worker threads. And this causes oversubscription to the cores. If we use one main thread plus 23 worker thread, typically we have a lower performance because the main thread does not do any work. It just enqueues tasks and then wait. So we get lower performance. If we have 1 plus n, we have 25 threads, we get a second effect, which is we have frequent migration of the cores, the threads that executing, because basically the main thread need to yield the cores that is using for the worker thread to start working, and basically this causes threads to migrate, and this migration can happen within the same NUMA domain, or this migration could happen between different NUMA domain. And what we found is that if you have like a smaller task granularity or smaller quanta, we have less frequent migration between NUMA domain. So if in the future we have a scheme that manages locality explicitly, we typically need to avoid this kind of migration, because basically we need to make sure that the core, after executing a certain task, if execute a dependent task, that it will execute from the same core, if not the same core, at least from the same NUMA domain. Now we have about 1/3 of the migration happen between different NUMA domains or NUMA nodes. So I'm sorry, I'm using interchangeably the word NUMA domain and NUMA nodes, but they are like that. So we did the same experiment for on Carver, and which is a different architecture. On Carver we have a larger memory, so we have 1 terabyte of memory. On Hopper we have most nodes, they have 32 gigabyte. So we tried to look at the scaling behavior for the base case versus the optimized one. For the two problems we discussed early on, and basically we see also improvement for the first and second problem with larger number of threads. So this improvement is up to 82% for 32 threads for problem 1, and about 53% for the other problem. But what is interesting about the behavior of these two problems on Hopper is that the first problem, which is P1, actually behaves the same way on Hopper and on Carver. By the same way, I mean here that the best performance was associated with better NUMA handling and also better load balancing. The only difference was that we start seeing more contribution of the management overhead, or the locking overhead, as we have 32 threads, so start becoming like 15% of the total execution time. The only difference we saw was for the other problem, which is B3, which is that if we combine both optimization, the performance was not optimal. So the best performance was associated with only load balancing technique. So if we can, in this particular case, the optimization effect were not adding up. And we believe that one possible reason of that is the way memory is managed. If this dependent on the I/O, typically we have a privileged NUMA node in most of the high-performance computing system. So if we go back here to this figure, we can see that the interconnect is typically connected to only one of the NUMA nodes. And most of the I/O, disk I/O happens through the interconnect. So if you put most of your data in the first NUMA domain, then you have like slightly better performance for the memory management part. So now I'm coming to the summary of my presentation. So to summarize here, we try to profile the code just to find what are the typical uses of the solver routines, and also to see if this use is optimal. And to do that, we looked at the performance outside the solver versus the performance within the solver. We applied two optimization strategy. The first one is round-robin NUMA location, which improved the performance by 11 to 15%. Also, we applied we tried to change the task distribution Quanta to improve the load balance of the workload, and overall we achieved 54%, up to 54% on Hover and 82% on Carver. And this set of optimization we applied are the ones that are possible when you have very little information in at runtime about the task that you are trying to execute. So basically, answering the question, can we do better? I think based on the results we are observing right now, we see a moderate scaling on 32 core Carver. We see 10 to 13x improvement. If we are lucky, we can double that performance, but this will require a very radical change because it will require more information about the tasks, about their location, about locality, about to do some dependency analysis between these tasks. And obviously all these approach can add some overhead. So will the net result be an improvement or not? It just require an exploration. So but ideally, if we have more information like what is the granularity of the task, we can tell, okay, we can group smaller tasks together, and instead of queuing one small task at a time, then we can queue group of related small tasks. If for large tasks, we need to have a smaller granularity. We lack this kind of information right now. Also, the location of the data can influence which core should we assign the execution of this particular task, depending on the locality information. Finally, if we have multiple queues, probably can reduce also contention, and probably can allow scaling beyond a single node. And in this case, we will be able to deal with the limited virtual memory in a much better way. So, so basically, we can apply some hierarchical task steering, where we typically try to finish all tasks within our queue. If not, we go to a higher level queue, and this higher level queue can be within the node. Otherwise, it can be on a different node. So we can do some kind of hierarchical task steering for this kind of workload. So with that, I end my talk, and I would like to open the floor for discussion, comments, and questions.
Okay, thank you very much, Khaled, for very nice presentation, very nice work. So please, remote attendees, if you have any questions, please write it here. And right now we are taking the questions from our group.
You guys have questions? No, I have several questions. Closer maybe. Khaled, very interesting. Lot of things to learn for us. Now, these optimizations, so can you say how transferable they are to other machines, how, it's probably a stupid question, but is it general enough to kind of start using it right away, or there are some assumptions about?
So I'm sorry, the voice has some jitter.
So these optimizations that you performed, how specific, how dependent they are on particular architecture, and whether how general they are?
Okay. So basically, for NUMA architecture, actually, this is very prevalent in many architecture right now, many new system right now. So if you look at the top machines in the US, you will find most of them are NUMA, except for probably BlueGene. And because basically, as we increase the number of cores, it is difficult to have a centralized memory that serve all the cores. So from architecture perspective, this is the kind of architecture that we have in many machines right now, and also it is what we expect to have in future architectures as well. So they are dependent on the architecture, but also they are general in the sense that most of the systems in the future will have these features.
Okay.
So this is one aspect of it. This is when we talk about NUMA. The other one is the workload distribution or load imbalance, and this is actually, even if we have we do not have a non-uniform memory access, we still have this issue, and we need to have a load balancing scheme. So this is a general problem if you have many cores that you want to scale your application to. So as you increase the number of cores, few things need to happen. The first one is that you need to avoid having a centralized queue. So one queue that serve all the cores, because this is an unscalable approach. The other thing is that you need to have better knowledge about the task granularity so that you can evenly distribute the workload, especially that your workload is composed of various granularity of work. So you may have a task that is that requires millions of cycles. Some of them require only a few thousands. So you need to have information to have better load balance, and this is an attribute mostly of your computation, not an. I would expect this to happen on all kind of architectures.
Okay. So my second question is about. So, and that's probably Zhenya can comment. I see he's calling in, maybe Michael. In principle, well, these two tasks are really quite small, so I'm really impressed that you were able to speed them up so much on a larger amount of course, because they are on a small size. And so I understand that profiling larger jobs is harder because we do have to deal with memory management. But on the other hand, I was thinking that probably for larger jobs, we will have maybe better pattern of BLAS using, of MKL using, because everything, matrices are larger and jobs are kind of, time demanding jobs are more uniform. We will see more of, the same, and we will see less of irregular calls. We will have the pattern of, what do you call it, signatures will be more uniform, and you will have fewer jobs appearing. So I don't know, maybe Zhenya can comment on that, or maybe you can also comment.
Yeah. So basically, I avoided for now working on the larger problems for multiple reasons. I saw some weird behavior or unexpected for me. So basically, on Carver, for instance, we have 1 terabyte, but still the memory management part tried to access the I/O, and this caused the application to fail because it was taking an extended execution time. So I delayed working on that for two reasons. The first one is that it wasn't clear to me that this is the approach you would like to have. So the virtual memory management, this is the approach you would like to have if you want to scale beyond a single node, because most of the time people try to avoid I/O and to try to avoid also explicit virtual memory management. So I didn't want to put effort in that before seeing if you're committed to continue with this approach, which is unlikely to scale beyond a single node. There are other approaches that can help you to scale beyond a single node, but it will require radical change, or at least the use of other tasking library instead of having your own one. But in general, the issues we discussed here are like orthogonal to the issues that you will have if you go beyond a single node. But I cannot have also a definite answer before having like a complete set of experiment for that.
So I think that's probably what we should discuss in more what we should discuss during the SciDAC time. Find some time, because I will be there and Evgeny is there and other people are coming too, because that's something that yeah, we would really value your input, and we do not have full picture of where we want to go with this course. So I think that probably would be important topic to discuss. And it's good that we have the seminar, so we can think before the SciDAC, and then we're a little bit primed with what you've done, so we can have more specific discussion.
Yeah, and I see there are some questions. So I think first question was from Michael Wormit. So let's see. Okay, how can I cannot read anything. It's so small. Okay, wait a second. What is it? Seriously. Okay.
Maybe try to make this window bigger, maybe?
Yeah, I'm trying, but I cannot see
No,
how.
the window, the whole window.
The whole?
Yeah. Because that's good.
Wait. It is. Okay, so I'm reading the question from Michael Wormit. So he says, "Hi, a really interesting talk. What utilities did you use for your analysis?"
So basically, I did that manually because there is no analysis tool that will distinguish between like two calls to the same function with different arguments. So I instrumented the code manually to get this information. So there is no tool that will allow you to do this. Unfortunately, there is no tool that will allow you to do this.
Okay, yeah, and the second question is from Samuel. Does the typical Libtensor QChem user turn off NUMA, EA make the memory performance uniformly bad?
I'm sorry, can you repeat the question again?
Yeah.
That's probably for
Zhenya. Yeah, does the typical Libtensor QChem user turn off NUMA, EA make the memory performance uniformly bad? So basically, yeah, I think it's more question not to you, but probably to Zhenya. Yeah. So Zhenya, I don't know if, I think you're unmuted. Let me see if you're muted.
Hello. So you said that the question is not for me, is that right?
Yeah, I think with this question, yeah, I think it maybe Zhenya cannot comment on it. Yeah.
Hi, can you hear me?
We can hear you barely. I mean, we cannot really hear you.
Okay.
Speak loud.
Can you hear me now?
Yeah, now it's better, but speak louder, please.
Okay. Okay, I didn't really understand the question. So maybe you should say it again.
Okay. Does the typical Libtensor QChem user turn off NUMA? So basically, I think it means that do we usually turn off NUMA? I don't know what NUMA means.
Well, we just don't have NUMA support at all.
Okay. Yeah. So yeah, okay. Yeah, and I think
so actually, whatever when we allocate memory, whatever malloc gives us, what we get. But because we do that from the main thread, my assumption would be that the version of malloc would be local memory, so it would stick to node 0 or whatever. Typically, but because we allocate a lot of memory, probably it goes over. So, yeah, changing the strategy to something like round robin should be fairly easy to do.
Okay, thank you. Yeah, and I think I see. Yeah, and I also can see the comment from you, which you say that we could try to run an array job to make more computations and have a smaller data set, which makes sense, yeah, because we have this array in Cholesky, and basically we use less memory, but it's still a lot of computation. So maybe it will be like, yeah, it will be easier for you to profile such jobs.
Yeah, it's true.
Yeah, and someone I think he's following up. He says there is a BIOS option for each machine. You can enable it to randomize memory addresses. If addresses are randomized, you see roughly uniform memory access, but it's dramatically suboptimal. So I think Samuel tries to say that. I don't know. I can actually unmute him. Maybe it's easier if you. Yeah.
So another approach to achieve the same thing, I guess.
Right.
So it's a uniform randomization. So basically, as we said earlier, we have two benefits of NUMA. The first one is to improve bandwidth if we distribute the data set evenly across NUMA node, and the other one is if you respect NUMA locality and basically most of the time you get stuff from your own NUMA node, then you get a lower latency. So if you do not have enough information, you can get away with the first benefit, which is the improved bandwidth by having a distribution. Whether this distribution is through a library that do a round robin or a kind of randomization, yeah, I think these are all valid approaches.
So my question really got to the heart of how nurse users typically use the machines. They use them in a manner that's been optimized for NUMA. And the question really is, how do most Libtensor or QChem users configure their machines? Do they configure them for uniform access, or do they configure them for the higher performing but harder to program non-uniform access?
So basically, on nurse you do not have the luxury to configure your node the way you want. It is always NUMA by default. So I'm not sure if this is answering your question or not, but
the question was really for Anna or Evgeny, if they've gotten any feedback from their users as to how they typically use their machine.
Well, so the users would configure their own nodes. We really don't know. I think, well, the computers that we have in our cluster at USC, most of them are the older ones. Don't even have NUMA. They just have one node. But the newer ones, I think they do. And Dmitry, how did you configure them? Did you enable the default mode, which is, I don't know, it's probably the uniform one?
Okay. Actually, I think the only thing which I changed were like default BIOS options for our new machines. I just turned off this hyper trading thing, And I don't remember if I saw in the BIOS, if I saw NUMA. I can look at it. Probably it's there if it should be there. And I don't know if it's now turned on or turned off. I don't know what's the default option.
So yeah, and so a short answer is we didn't experiment in that because our old machines didn't have this.
Yeah, I think our old machines, which we mostly use, most of the machines that you see, I think it doesn't have this option. And yeah, we can try to play with new machines and see how it really changes the performance.
Yeah, so, but not only BIOS, you need to make sure that the OS is supporting NUMA.
Mm-hmm.
And later on, when you start using Lib, so if the OS is supporting them, you need to have like libraries that allow you better control of distributing the dataset on different NUMA nodes. So all these need to be configured correctly to observe the performance benefit of NUMA.
So I think that would be another item on our action list before say that.
Okay.
Dima here will look up, exactly what we have, BIOS and system, and then we will come with specific questions, and you guys can give us advice.
Yes.
Yeah.
Okay.
One could also imagine running a benchmark before actually running an application that determines whether the machine is configured for NUMA or not, and we choose a different implementation based on that information.
Mm-hmm.
Yeah.
Okay. Okay, thank you. Thanks to you all for... Yeah, let me see if you have any other questions, and if you don't, we will thank all the presenters. Yeah, I think that was it. So, okay, thank you very much to everybody. Thank you to Khaled.
Yeah, so we will, continue thinking, and probably we'll get some email exchange, but I'm hoping, we will carve some time during SIDAC meeting to talk specifically about this stuff. And I also will be staying for Tuesday after main SIDAC meeting, so we can squeeze in maybe some more discussions. So, and thanks everyone, and especially thanks Khaled, and we'll be in touch.
Yeah, thank you everybody. Thank you. Bye-bye.